All right, let's get right into it. We're all surrounded by these incredible feats of engineering, right? Skyscrapers, bridges, massive ships. But have you ever stopped to think about what's actually holding them together? So often, it's a tiny seam of metal forged in a flash of incredible heat, a weld. And getting that weld perfect, well, that's not just a skill. It's a high-stakes scientific battle fought at a scale you can't even see.
I mean, that's the big question, isn't it? It's the kind of thing that keeps engineers up at night. The safety of our entire infrastructure, the integrity of pipelines carrying critical resources, it can all hinge on the quality of these tiny metal joints. So how in the world do you control a process that happens faster than you can even blink?
Well, the answer, it turns out, is hidden right inside the weld pool itself. And you gotta understand, this isn't just some puddle of molten metal. No, it's a superheated, violently churning microfurnace where temperatures can spike over 2,000 degrees Celsius. It's total chaos. And inside that chaos, a really complex chemical drama plays out, and its final act determines everything. And at the very heart of that drama are these little things called inclusions. Just think of them as tiny, non-metallic particles, like microscopic specks of dust floating in the molten steel. For the longest time, everyone thought they were just bad news, weak spots that could make a weld crack. But here's the twist. Scientists discovered that the right kind of inclusions in just the right size and number could actually be the secret ingredient to making welds tougher than ever before. The whole game then became about figuring out how to control them.
So, to solve this microscopic mystery, researchers had to think big. I mean, really big. The first clues didn't come from a welding torch at all, but from the massive, slow-moving world of industrial steelmaking.
And just look at the difference here. It's pretty mind-blowing. On one side, you've got ladle metallurgy. Chemists there have hours to carefully tweak and control reactions in literal tons of molten steel. It's a stable, well-understood process. And on the other side, a weld pool. We're talking a few grams of steel reacting in milliseconds in an environment of just insane turbulence. You couldn't imagine two more different worlds.
And this, right here, is where the genius really kicks in. Decades ago, researchers asked a pretty wild question. What if we could take all those well-understood chemical rules from the giant steel mill and shrink them down? Could we actually adapt them to predict and maybe even control the chaos happening inside that tiny, violent weld tool? It was a massive leap of faith, really, building on decades of existing knowledge to tackle a brand new frontier.
So, with this new way of thinking, the goal was clear: create a predictive model. They needed a way to forecast what kind of inclusions would show up based on the ingredients you put in. And their first big breakthrough came from good old-fashioned classical chemistry.
This led them to a theory called sequential oxidation. And here's the key idea. As that super hot weld pool cools down, not everything happens at once. The elements that are most reactive, the ones that are really eager to grab onto oxygen, they go first, forming a core. Then, as the temperature drops a bit, the next most reactive element comes in and forms a layer around that core, and so on and so on. So the final inclusion isn't just one thing, it's a layered structure, kind of like a microscopic jawbreaker, that tells the whole story of how it was born. Now, to test that theory, they used a tool that looks something like this. It's called a deoxidation diagram, and you can basically think of it as a scientific map. By plotting how much of an element is in the mix versus how much oxygen is available, researchers could predict exactly which element would form an oxide and at what temperature. It let them map out the recipe for an inclusion before they even struck an arc. This was huge. It was the first time they could reliably predict the chemistry of that microcosm. Okay, so those thermodynamic maps were an absolute game changer, but they were static. They told you the destination, not the journey. The next revolution needed a totally new tool, serious computational power. The kind that could turn those static maps into dynamic, step-by-step simulations. This flowchart here kind of shows the logic behind modern software like thermocalc. What the computer does is it starts with the initial chemical mix at the peak temperature. Then it simulates the cooling process in tiny little steps. It calculates all the chemical reactions at one temperature, adjusts the recipe, and then does it all over again for the next temperature step, degree by degree, all the way down to room temperature. It's literally like watching that whole chemical drama unfold in super slow motion.
And here it is. This is the payoff. This graph plots the model's predictions against the actual composition of inclusions they measured in real-world welds. Now, if the prediction was perfect, all those dots would land right on that straight line.
Look how close they are. That 0.85 correlation, that is a stunning achievement. It proves that by building on all that legacy research, these modern models can now accurately predict the outcome of that chaotic, millisecond-long process. It's incredible. So now we can accurately predict what inclusions form. The next logical question for any scientist is, okay, what happens to them after they form? Because the life of an inclusion doesn't just end at birth. It's a dynamic, evolving process happening inside that liquid steel.
So, the life of an inclusion has a few stages. First, they're born. That's nucleation. Then, they start to grow as more atoms find their way to them. But remember, they're in that turbulent weld pool, so they're also bumping into each other and merging. And finally, this really interesting process called Oswald ripening kicks in. Think of it like a snowball effect. The bigger inclusions actually start to cannibalize the smaller ones to grow even larger. Understanding this whole life cycle is the next big step in truly controlling a weld's final properties.
Which, of course, brings us right back to the ultimate goal. All of this deep, fundamental science, from classical chemistry all the way to supercomputer modeling, it was all driven by one practical purpose: engineering stronger, tougher, and more reliable welds.
And this right here, this is the holy grail. It's a microstructure called acicular ferrite. Just look at that beautiful, interwoven, almost basket weave-like structure. This is what gives a weld incredible toughness and makes it resistant to cracking. And how do you create it? You guessed it, by perfectly controlling those tiny inclusions we've been talking about. They act as the perfect little seeds for these tough, needle-like crystals to grow on. Master the inclusions and you can engineer this superior microstructure on demand.
So why does all of this really matter? Because this deep understanding lets us design the next generation of welding materials, things like filler wires, with incredible precision. We can literally write a chemical recipe to produce the exact inclusions we need to get that tough acicular ferrite. And that means stronger bridges, safer ships, way less costly trial and error for manufacturers, and a powerful launch pad for future innovation. All of it built on a foundation of research that stretches back for decades.
It's just a powerful reminder that sometimes the biggest engineering challenges we face are solved by understanding the absolute smallest things. The journey from a giant steel ladle to a computer model of a single inclusion shows how science can truly tame chaos. It just makes you wonder, right? By mastering this microscopic world, what other huge macroscopic challenges are now within our reach?